Good afternoon, everybody, and I'm here. First thing I want to report to you before we get started on this problem is that a lot of math problems are designed to work. I'm sure I'm not telling you guys anything you don't already know, but some of these so-called challenging math problems, somebody starts from an obscure result or something that may be slightly difficult to prove, and then creates an arithmetic problem. That's exactly what I've done right here. Now, what I have for you is a lemma. Now, when I was going to school, a theorem was something, a more substantial result than a lemma. A lemma was something you could prove, but it's not quite as momentous, shall we call it, as a theorem. What we have here is a lemma that's the basis for solving our problem today. And I can do another video on the proof, but for now, I'll just state it as a fact. The lemma states, and you can read it, that if you take the product of 4 consecutive natural numbers and add 1, and then that is actually a perfect square, as illustrated by this lemma. Now, there's a couple of ways to prove it. At least 2 that I know of. You could do induction, prove it that way, or you can actually prove it using the difference of 2 squares formula. Believe it or not, k times k plus 3 gives you this 3k term right here. And also k plus 1 times k plus 2 also gives you a 3k linear term. It turns out that ends up being the difference of 2 squares. It's not so obvious actually looking at it, but in any event, we'll go ahead and take this as a fact. And I've shown you the special case here. If you substitute 2 in there, in every place you see a k, you end up with root 121, excuse me. And you can see that the right-hand side equals to 11 when you substitute 2 in. So anyway, enough about the lemma. If anybody wants to see why that's true, I'd love to produce a video for that also. But let's get along with the problem here. Okay, now our goal today is to evaluate this monstrosity here, this radical. And of course, this is a no calculator problem. That wouldn't be any fun, right? Substituting into the calculator. I can see even the baby has an indignant look here. He's going, "Are you serious? We're not going to use a calculator for this." But now, so let's look at this real quick and see how this lemma might come in handy. And I'll repeat myself here. Imagine your consternation trying to solve something like this without a calculator if you didn't have some intermediate result to work with. And this is a plus sign right here. That's definitely a plus sign right there, for sure. That's a plus sign. You might think, well, you got these consecutive multiples of 4 that are multiplied and all of a sudden you're adding, but this is correct the way it's stated. Now, that's another key aspect of this problem. These aren't consecutive natural numbers right here, but they are consecutive multiples of 4. Okay, again, this result up here, the lemma says if you have 4 consecutive natural numbers, add 1 to that product, it ends up being a perfect square given by the right-hand side. So you can already see how the lemma makes this problem sort of melt in your mouth. There's going to, since these are all multiples of 4, there's going to be 4 4s in there, or 4 to the 4th, which we can factor out. Now, to save time, I've just done that for you. So let's go down here and use my high-end way to do animation, which is to delete the empty spaces here. Here we go. I'm pressing the delete button. I'm not ashamed to admit there. All right, now, so as you can see, folks, you see what I mean? Melts in your mouth here. You have 4 to the 4th right there because that was 4 multiples of 4. 4 times 60 is the 240. 4 times 61 is the 244, and so on. All right. And conveniently, and that's why the problem is contrived or designed to work, I wrote 256 in there because that is 4 to the 4th. Now note how the 4 to the 4th, when you square root it, becomes 4 squared. And now we just appeal to the lemma. You know, the square. This would be quite difficult without the lemma. I don't know how I would do it if we didn't have the lemma, but the lemma prevails right here, and you can see that the 16. And then again, I'm just using the result of the lemma, k squared plus 3k plus 1. And now I say no calculators. I got to admit I did use a calculator right here, but at least we've got it to a state where if we had enough time on our hands, we would not need a calculator to perform this computation. Okay. So again, I kind of went against my claim that it's a no calculator problem, but plugging this in to the calculator, certainly, where's the fun in that? And down here, at least you've got it to a manageable state where you could give it to a class of middle schools and they could perform that computation. Hope you enjoyed the video.